In this video, we're going to learn how to use the utility maximization process to derive a consumer's demand curve. Muriel purchases two goods, sketchbooks and pencils, where X denotes the number of sketchbooks purchased and Y denotes the number of pencils purchased. Muriel has an income of $40. The price of a sketchbook is P and the price of a pencil is $1. Her utility function is X plus 4Y to the 0.5. Our goal is to determine her demand for sketchbooks. What do we need to know in order to answer this question? Turns out all we need is the utility function. How are we going to solve this question? Just like a utility maximization problem, the only difference is we might not have prices for either good or a value for income. Now in this particular question, we do have income and we have the price of a pencil, but we do not have the price of a sketchbook. The question would be much more difficult if income and pencil price were unspecified. Difficult from an algebraic perspective because the demand curves would have a lot of variables hanging around in them. So let's see what it looks like to solve a demand question. So here's what we know. We know the demand function, the price of X, the price of Y, and Muriel's income. Our goal is to find Muriel's demand for sketchbooks, which is good X. I think from my perspective, when you're deriving a demand curve, it's always a good idea to start with a plan. So our goal is to find the demand for sketchbooks, X. So we're going to use the tangency condition to figure out how Y depends on X. Then we'll substitute this relationship into the budget constraint and solve for X. So the first thing we have to do is we need to find the marginal utilities. The marginal utility of X is equal to the partial derivative of the utility function with respect to X, which is 1. The marginal utility of Y is the partial with respect to Y. So Y appears in the second term. We're going to bring the 0.5 down, and it's going to turn that 4 into a 2. And then we have Y to the 0.5 minus 1, which is negative 0.5. From there, we can form the tangency condition and write down our budget constraint. So the tangency condition says that the ratio of marginal utilities equals the ratio of prices. So we have 1 divided by 2y to the negative 0.5 is equal to P, which is the price of X, over 1. I'm not going to simplify this yet. I'm just going to call it equation 1, and we're going to deal with it in a minute. I can also write down my budget constraint. Budget constraints always have the same formula. It's the price of X times X plus the price of Y, which is $1, times Y is equal to income, which in this case is $40. We'll call that equation 2. So using the results of the tangency condition and the budget line, we are going to solve the tangency condition for Y. So this is going to take a little bit of a simplification. The first thing I'm going to do is I'm going to notice that Y is raised to a negative power, so I'm going to move it up to the numerator. So I have Y to the 0.5 divided by 2 is equal to P. Now I've noticed that sometimes students, when they move a term like Y to the 0.5 up to the numerator, they accidentally drag the 2 up along with it, causing all sorts of mathematical problems. That 2 is not raised to a negative power. It lives in the denominator. You can't pull it out of there just because you feel like it. So what are we going to do from here? I'm going to multiply both sides of the equation by 2 in order to isolate Y to the 0.5. So I have Y to the 0.5 is equal to 2P. And then I need to find Y. So I'm going to square both sides of my equation. And I'll get Y is equal to, not 2P squared, but 4P squared. And the reason is both terms in this parenthetical are raised to the power. That includes both the 2 and the P. We'll call this equation 3. So we're almost done. We know how Y depends on P. And we sort of extracted all the information we could out of that tangency condition. So what we need to do now is we're going to take 3, that relationship between Y and P, and we're going to plug it into the budget line, which is equation 2. And by doing that, we're substituting in what we know about y so that we can solve for x. So I have x times p is equal to, x times p plus y, where y is 4p squared, is equal to 40. Now, don't get lost at this point in the process. So far, it looks just like utility maximization, except we have this funny price hanging around that's unspecified. Don't solve this thing for price. That is not what this question is asking us. We're trying to find Muriel's demand for sketchbooks, which is our x value. So we solve this for x. So I'm going to write x times p is equal to 40 minus 4p squared. And then I'm going to divide both sides of my equation by p and conclude that x star, which is like the way of representing the fact that this is a demand of p. So this is not multiplication, but it's function notation. I'm saying x depends on p in the following way. It's 40 minus 4p squared all over p. I see no reason why this should be simplified further, so we can call this our final solution.